Chapter number 3 is going to start talking about the makeup of the atom. Now, you just got done taking a quiz over the elements, so what we're going to do is we're going to start looking at that atom. Some of the things we're going to talk about today is you're going to describe the structure of that atom. You're going to compare and contrast those 3 subatomic particles, and then we're going to look at a little history as we talk about the development of that atom. Again, we talked about John Dalton, we talked about his hypothesis about the atom, and we said his model of the atom was this hard, dense sphere that was completely uniform throughout. Now, his model of the atom basically was this. Again, just a solid sphere that was going to be completely uniform throughout. Now again, as technology advanced, you're going to find out that, oh my gosh, it was probably about 100 years go by before technology improved enough that J.J. Thomson was able to discover a couple of different subatomic particles. Instead of that atom being completely the same all the way through, he discovered that there was a positively charged particle, and that positively charged particle he called a proton. He also found out that there was a negatively charged particle, and that negatively charged particle was called an electron. He developed a model of the atom that he called the plum pudding model. Now, the plum pudding model was basically this. You had an atom that was circular in shape. Now, we had this filling inside, and this filling within the atom, we're going to say, was completely positive. Okay, so we're positive from there all the way around to there. Also, we said that there were these negative particles, and those negative particles were the electrons. Now, the reason why it was called a plum pudding was really back then in the 1900s there was a delicacy called plum pudding, which basically was vanilla pudding with a bunch of raisins in it. The vanilla pudding, that would represent this complete positive filling. And then every time you take a scoop and you see a few raisins, each raisin would represent an electron. More commonly today, his model of the atom is known as the chocolate chip cookie dough. Again, when you put your eggs and your flour and your sugar and all of that together and you beat it up, you kind of get this yellow dough mixture. That really would end up being the positive. And when you add your bag of chocolate chips, each little chocolate chip would represent an electron. Now, in 1911, Lord Rutherford comes along and he does this gold foil experiment. And in that gold foil experiment, we have an alpha particle emitter. Now that alpha particle emitter, what I'm going to go ahead and tell you about it, was this was completely positively charged. So you had this positive radiation that was being shot out, and as that positive radiation was being shot out, notice what happens. Most of it ends up going straight through. Now, there were a few particles that got deflected off to this side. There were actually a couple of particles that got deflected back. So what he did was he thought, we need to look within this atom. And when he looked within the atom, again, let's go ahead and look at this here. We have this positive radiation. Positive radiation. And again, each one of these is going to be positive. Now, here's the thing. When you follow this line, look what happens. Goes all the way through. You look here, all of a sudden, it goes all the way through. Now, if I follow this fourth line right here, this fourth line starts heading right towards the center of the atom, but before getting to the center of the atom, it actually bounces off. And that was very important information to Rutherford, because he knew that if this line was positive, the only thing that was going to cause a positive to bounce off was something else that was positively charged. So he thought Thomson could not be correct in saying that this whole thing was positively charged. He thought that that center of the atom had to be positively charged. So instead of the positive being all spread out, he thought that it had to be condensed or compact in the middle and not completely spread out. So he came up with 2 conclusions. The first conclusion, because most of those particles went straight through, he said most of that atom was empty space. Now, the second one was the big one, and he said that that atom has a dense positive core. which leads us to his model of the atom. His model of the atom looked like this. So again, we have our circular shape. We have our center of the atom. And instead of the positive being completely spread out, he said that that positive was packed there in the middle. On the outside were the electrons. So again, he still agreed that the electrons were on the outside, but the positive was packed into the middle of that atom. 1913, so a couple years go by, and Niels Bohr comes along. And what he said was, well, if you're just saying that those electrons are sitting there, what's going to keep them from crashing into the center of that atom? We know that positives and negatives are attracted to one another. So what he said was, you know, those electrons, instead of just sitting there, those electrons have to be moving. So again, he had the nucleus of the atom. But what he said was those electrons that were on the outside had to be moving. So they weren't just going to be sitting there. So his model of the atom is kind of like maybe a picture that you've seen before, where again those particles are moving around the outside. So again, electrons are now moving in a circular path. Now, one thing that I'm going to do is, again, if I kind of draw a circle around this, you're going to kind of see that there would be kind of one ring, and that's going to be important in our last model, or our current model of the atom. Was Niels Bohr really said that there's only kind of one circular path for these electrons in 1913. Our current atomic model, there was actually another piece of the puzzle that took about 21 more years, is about 1934, that final piece of the puzzle was found. Scientists found that the negatively charged particles had different energy levels. Again, if you go back and you think of that picture that I just had on the board, this one here, where again we said there were multiple energy levels, Niels Bohr said that there really would have only been one energy level. And today's model has different levels of energy. And those different levels of energy are going to be called orbitals. And what they are designated energy levels, different amounts of energy at each level. So that brings us to our current atomic model. Our current atomic model has a center of the atom. And the center of the atom is going to have your protons. Now we'll go ahead and get to the symbols in just a little bit, but the P positive, that is going to be my neutron. Also in the center of that atom is going to be your neutron, and that's going to be represented by N0. Now, this is where the difference in the current model and Niels Bohr's model come into play. Is there's a ring there. Here is a ring here. And I'm not going to draw all of them. I'll just go ahead and draw one more. Okay. So you have your electrons on the outside in these different energy levels. Okay. Or we could also call them orbitals. Okay. So again, electrons are on the outside in energy levels. The center of that atom, the center of the atom is going to be referred to as the nucleus. So this is our current model of the atom. And like I said, I have three levels, or three different energy levels that are showing up here. In reality, there are about 7 of them. So what's in an atom? An atom is going to be made up of 3 subatomic particles. The first one is going to be a proton. And a proton is any positively charged particle, and again, it's represented by P positive. Electrons is just going to be a negatively charged particle, represented by E negative. And a neutron is a neutrally charged particle, represented by N0. The center of that atom is going to be called the nucleus. This holds your protons and your neutrons, and then on the outside where your electrons are, in those 7 designated rings, are going to be orbitals. Or now again, as I go ahead and I talk about this and looking at this nucleus of the atom, one thing maybe that I forgot to mention would be this. All of the mass of your atom comes from the nucleus. protons and neutrons are extremely large in charge. What you're going to find out, or what we'll close with today, is you're going to find out that that electron is about 1,800 times smaller than a proton or neutron. So all of your mass is going to be found within the nucleus of an atom. So again, the key thing here is, so what makes gold different from silver? What they just said in the video was the number of protons determines the chemical identity of the element. And that chemical identity we're going to refer to as the atomic number. Your definition for atomic number is it's the number of protons in the nucleus of an atom. Now, because all atoms are electrically neutral, we're also going to say that this is the number of electrons. So if you have 10 protons, you have 10 electrons. 10 positives will be canceled out by 10 negatives. So your atomic number will be your number of protons and your number of electrons because an atom is electrically neutral. When you look at a periodic table, this whole number right here is going to be the atomic number. Anytime you look at a periodic table, find the whole number, and that will be your atomic number. Now, atomic numbers are a little bit different in each periodic table. The one that's hanging in my room, you're seeing that the atomic number is located in the upper right-hand corner. If you have downloaded one on the internet, this is one that I have. So again, right here, zinc has an atomic number of 30. Oxygen has an atomic number of 8. Tellurium has an atomic number of 52. So the thing is this, every time you look at a periodic table, find the whole number, and that will represent your atomic number. Or, for example, tellurium, 52 protons, 52 electrons. So the question says, how many protons and electrons are in copper? Go ahead and looking at this periodic table, find copper. It's located right here. The whole number, number 29. Number 29 is going to mean that we have 29 protons and 29 electrons. Now, the second one says, what element has 74 protons? So again, if I go to the periodic table, going to the periodic table, again, we're going to find the atomic number, and finding that atomic number, we're going to find number 74. 74 is located right there. Kind of hard to read, but it is one that you had to know for your elements quiz. W is going to be tungsten. So tungsten's going to have 74 protons. Like we said earlier, the mass of the atom comes from the nucleus. And again, what's in the nucleus? It's your protons and neutrons. Electrons are extremely small. It takes about 2,000 electrons to equal the mass of one proton. The mass of the protons and neutrons together is going to be referred to as your mass number. This is the total number of protons and neutrons in the nucleus of an atom. Or if you want, we could say the mass number is the mass of the nucleus. So mass number will equal protons plus neutrons. Now, through some experimentation, scientists found out that there are different kinds of each element. For example, there are 3 different kinds of hydrogen. There are 3 different kinds of carbon. There's, in this case, the example we're going to be looking at, potassium. Potassium is going to have 3 specific kinds of potassium. Those are K39, K40, and K41. Now, K represents potassium. The 39, 40, and 41, those are going to represent the mass number. Again, 39 for a mass in the nucleus, 40 for a mass in the nucleus, 41 for a mass in the nucleus. Now, because it's potassium, find potassium on your periodic table. When you find potassium on the periodic table, it's located over here to the left. Let me move that out of the way. Right there. There's K, potassium, number 19. So we know that potassium is going to have 19 protons. That's potassium, 19 protons. potassium there, 19 protons. Because an atom is electrically neutral, 19 electrons, 19 electrons, 19 electrons. The difference in these different kinds of potassium comes from the number of neutrons. And we find the number of neutrons by taking the mass number minus the atomic number. The number of neutrons, what we're literally going to do is we are going to take this mass number for this first one here, 39, and we're going to subtract away the atomic number, 19. And for this one here, we're going to find out that there are 20 neutrons. For this second one, what we'll do is we'll go ahead and take 40. We'll subtract away 19, and for this one here, you'll find out that there are 21 neutrons. For this one here, or the last potassium, you'll take 41 minus 19, and you'll end up with 22. So 39 minus 19 gives me the 20. 40 minus 19 gives me my 21, and 41 minus 19 will give me my 22. Well, let's look at one more example. This one says determine the number of protons, electrons, and neutrons in gold. So this question says we need to find the protons, electrons, and neutrons for gold. Now, the protons and electrons, that one's going to be very easy. All we do is we go ahead and come to our periodic table. When we come to our periodic table, it says gold is number 79. Because it's number 79, what I can go ahead and do is I can go ahead and say, okay, protons, 79. Electrons, 79. Now, neutrons, we said we have to take our mass number and subtract away our atomic number. But I don't have a mass number. What you do is this. Go to your periodic table. Now, I know this one is kind of hard to see, but I do have it off to the side here. There is this big, long decimal number underneath the word gold. Same thing on mine. The big, long decimal number on this one, or on my periodic table, will be below the symbol. But when I look here, it says the mass is 196.96. 196.96. So what we're saying is if a mass number isn't given, look at the periodic table and round the atomic mass to the nearest whole number. To the nearest whole number. So we said for gold, the number was 196.96. So to get that to the nearest whole number, we're going to say that that is equal to 197. And with that being equal to 197, what we can now do is subtract away the atomic number, 79. And when I take 197 minus 79, that will tell me the number of neutrons. So 79 protons, 79 electrons. We took that rounded whole number that was on the periodic table, 196.96. We subtracted away 79 to get 118. So there will be 118 neutrons. So again, if a mass number is given, use it. If a mass number isn't given, look at the decimal number on the periodic table, round it to the nearest whole number, and use that as your mass number. So a little bit in review. Particles, charge, mass, and location. The first one's going to be a proton. And again, protons are positively charged, and because they are large in size, we're going to say that they have a mass of 1, located in the nucleus of an atom. Electrons, those are the negatively charged particles, and we said protons and electrons were the same, meaning that if there's 10 of these, there's going to be 10 of those. But the mass is greatly different. It's about 1,840 times smaller than a mass of a proton. And we find these in the orbitals or the energy levels. And the last subatomic particle is going to be a neutron. A neutron has no charge. It is also found in the nucleus of an atom. and it has about the same mass as a proton.